In this video, I am going to walk you through some examples of plate count problems you might encounter on an exam. So we're going to do the same process we did in the plate count video, but I'm going to add the things to it that you would have seen if we were doing this in a face-to-face lab. So the steps for analyzing plate count data are: number one, assess data quality, and I'll tell you what this is about. Two, choose your dilution. Remember, you're going to choose one of these plates. If these are all different Petri dishes from different dilutions, you're going to choose one. You count the number of colonies, and you're going to use that number to calculate the unknown sample size. So you have to choose one of these, and then do the calculation. Okay, so what does it mean to assess the data quality? Well, there are a lot of things, and it makes more sense if you have seen things that go wrong. So some things that can go wrong are like contamination on the plates. Is there fungus all over the plates when it should be little bacterial colonies? Are there 3 different kinds of colonies when there should only be 1? That's the kind of thing you're looking for. But also something that happens in serial dilutions is the dilution can have a problem. Serial dilution is a distinct, kind of unique thing in microbiology, and it has its own set of possible problems. So the way we look at it, remember, is we start with a 10 to the minus 1 dilution, and we use that to make the 10 to the minus 2 dilution, and we use that to make the 10 to the minus 3 dilution, which we see here because it was plated, it was put onto a Petri dish. We would use the 10 to the minus 3 dilution to make a 10 to the minus 4, and so on. Each time we make a new dilution, we are dividing the number of cells by 10. We're doing a 10-fold dilution each time. And what that means is we expect to see the number of colonies keep getting divided by 10. So if we go from 10 to the minus 4 to 10 to the minus 5, we should expect this to have 1/10 as many colonies as this. And this should have 1/10 as many colonies as this. So that expectation is something we have to have validated. When you look at your plates, they have to match that pattern. If they don't, there's a problem. Your lab partner screwed this up. And so you don't count the plates. You just write, there was a problem with the data. It has to be repeated. So what's the case here? Well, these are numbers that look a lot like real numbers you'd get in a lab. And what they show you, well, first of all, only one of these is between 30 and 300, and that's this one. And that is what we expect. Only one of them should be between 30 and 300. And so we expect the next one to be 1/10 of this. So we expect this to have 25 colonies. It has instead 15. So is that close enough or not? And then this one should have 1/10 as many colonies. So it should have 1.5. Or it should have 1/100th as many colonies as this. And so here you're starting to see that when you have small numbers of colonies, they don't line up very well. When you have small numbers of colonies, little experimental weirdnesses put noise in the data, and that's what this looks like. So instead of being 25 and 2.5, it's 15 and 3. So what we're thinking about is just a general order of magnitude difference. Do we see that? And we kind of do. If you were going to graph this on logarithmic graphing paper, on the semi-log graphing paper, these would line up pretty well. And if I give you an example on an exam with bad data, it will be more obvious that it is bad data. So as you are getting ready to go ahead and analyze some data, I just need to show you some better guidelines for, is the data good or is it a bad data set? Basically what you're doing is you're having observed data, so this is the real data you have, and then you have predicted. So based on this, we would start with whatever countable number we have. So that's 253. And then we would say, well, what's the predicted number? This should be 25.3, and this should be 2.53. So then for each of these, we would look at the ratio. This divided by this. And so we start off with 1. And then for this one, I'm using a calculator, and I calculate that this divided by this is 0.59. What we want is 1. What we would want is for this to be perfect. We want this to line up with what we expect, a 1/10 dilution of this. We don't get that. So is that bad? You know, that's not great. Then what about this one? What's the ratio here? 0.3. So using these data that I made up, I need to use a calculator to analyze them. So what we want is the same ratio. We want the ratio to be 1, right? We want our observed data to match the predicted data, and it never will in reality. So what you're really looking for is there a trend in the ratio? Is there a trend? Does it keep getting worse? And you would know it were bad data if you find this 0.59 and the next one would be like 0.2 and the next one would be 0.1. If it keeps getting worse in the same direction, then it's bad. If it keeps getting worse, in the same direction, it's bad. So let me give you some better examples of what bad data would look like. So here we'd start with 253. So these would be observed, and this would be predicted, and this would be the ratio. So predicted 253, ratio 1, perfect. So now let's do some math, and I apologize, I just need to use a calculator. And then this one, the predicted would be 25.3, this would be 2.53, 0.253. So what numbers do we actually get, and what are the real ratios? Okay, so I had to use a calculator to find these ratios. And what I see is the ratio keeps increasing. So the ratio of observed to predicted keeps increasing. That is a clear trend. It goes 1 to 1.5 to 3.5 to 7.9. That means there's a systematic problem with the dilutions. This person did the dilutions wrong. They were doing close to 1/5 dilution instead of 1/10 dilution. Here, even though it's not pretty, there's no obvious pattern to the ratio. The ratio is like, well, we start at 1, this one's below 1, this is above 1. So there's no systematic error here. It's just ugly data. So that's what I would recommend doing. And if I'll make sure that the data you get are easier to calculate. So numbers that you could do in your head. And also, this should look very different, right? Like I'll give you prettier numbers if I'm going to make you decide whether the data look good or not. Okay? So you won't be dealing with 253 and 40 and 9 and that kind of thing. Okay, let's get back to the calculation we were doing, and let's look at the plates we had. Okay, so we choose the dilution. That's the one where we have between 30 and 300 colonies, and then we do the calculation. So how do we do the calculation? We take this number, 253 colonies, divide it by the volume of dilution that was put on this petri dish originally, and that is always going to be 0.1 milliliters. And then we multiply this by 1 over the dilution factor. And the dilution factor of this one is 10 to the minus 4. And so we just need to go through this. This is the same as having 253 colonies over 10 to the minus 5th. And that would be milliliters. And that is literally what you would kind of get if you had put 10 to the minus 5th milliliters of the original sample onto the Petri dish. This is what we would predict we'd see. So that's, we need to get colonies per milliliter. So basically, we're going to try to do this, 253 times 10 to the 5th. That's what we would actually do. If you divide this by 10 to the minus 5, it's the same as multiplying by 10 to the 5. And so we're trying to get this in scientific notation, so we're going to take a decimal point from the right. So we could imagine this is 253.0. So the decimal point is here. Move it over once, twice, and then we would have scientific notation. So this goes up by 2. So we get 2.53 times 10 to the 7th. And remember, the units are not going to be colonies per milliliter. They're going to be colony-forming units per milliliter. So the unknown original sample with its unknown population size, this is the population size. This would be the answer. But remember, it's a 3-step process. It's not just this calculation. It's assess the quality of the data. If the data don't look good, you don't analyze them, throw them out, and start over. And then we have to choose the correct dilution, and then we can do the calculation. So let's do another example. Okay, so these are the numbers your lab partner gives you. Your lab partner made these plates yesterday, put them in the incubator, and you need to analyze the data. So you have 4 plates with these dilutions, and you count this many colonies. Go through the 3-step process. Assess the data, choose the dilution, and then do the calculation, and come back and see if you do it the same way I did it. So pause the video, do your calculating, and then compare it to mine. So I assess the data. I ask, is this roughly 1/10 of this? 1/10 of this is 5.5. It's pretty close to 7, certainly on the right order of magnitude. What's 1/10 of this? 0.7. It's less than 1, so we're not surprised to see 0, and then this would definitely be 0. So the data look good. We choose this one because it's between 30 and 300 colonies, and then we do our calculation, and we do 55 colonies divided by 0.1 milliliters times 1 over 10 to the minus 1, and that's the same as 55 times 10 to the 2nd power. So I skipped a step, but I multiply these two together, and that would be 10 to the minus 2, and that's the same as multiplying by 10 to the plus 2. So then to put that in scientific notation, again, I move the decimal point over 1, so this increases by 1, so it's 5.5 times 10 to the 3rd. And then what are the units? To get full credit, you of course must use the correct units, and those would be colony forming units per milliliter. And you can abbreviate CFUs per mil. No one would confuse that with anything else. Let's do another one. Here we see new numbers. So we came back again the next day, and our lab partner has given us more plates to count, and we need to do another calculation. So remember, what are the 3 steps you're going to do? You're going to assess the quality of the data, then you're going to choose the right dilution, then you're going to do the calculation. So go ahead, pause the video, go through that whole process, and then pay attention to what I do. So I assess the data quality. And the first thing I really look for is what are the ratios between these numbers? What's the ratio here? Well, if you divide 155 by 3, you get something like this. Or by 5, sorry. That looks like about 1/5. And you can use a calculator if you want. So that's about 1/5. If you divide that by 5, you get 7. So that's about 1/5. If you divide that by 5, you'd get 1. So that's about 1/3 is what it actually is. All of these should be 1/10, right? These are 10-fold dilutions. So if that's 155, that should be 15, and that should be 1, and that should be 0. That's not what we see. We see 150, 35, and then 6, and then 2. This really jumps out at me as being wrong, but also the fact that we have colonies on all these plates, and that we have 2 plates with numbers of colonies between 30 and 300. That shouldn't be possible if the dilution works correctly. So I look at this, and from the fact that I have 2 in that correct range of 30 to 300, I know this is not a 10-fold dilution. Something went very wrong. My lab partner needs to be yelled at or convinced to be more careful. So the data are not good enough to be analyzed, so we do not analyze these data. So our answer is try again, pal. Let's do another one. Okay, we're back with new plates that our lab partner has made for us. They tried again. So let's remind ourselves what we're seeing here. This is too numerous to count, so there were just too many colonies. It was clearly not between 30 and 300. Same with this one, same with this one. And in this one, we counted 453. Yes, we really did count 453 colonies. That is completely possible. The colonies are very small, and that takes a long time, and we would be angry at our lab partner if we had to count that high. Especially because this is not between 30 and 300. So if we're assessing our data quality, we can't. The data might be fine. If they had done a 10 to the minus 5 dilution, if they had done 1 extra dilution, maybe they would have had 45 colonies. We don't know. But we're basically stuck because none of these is between 30 and 300, so we can't analyze the data. We would have to try again. So let's do another one. This is a slightly different situation where we come in and look at the plates and count colonies, and this time this one is in the correct range. The problem here is it's hard to assess the quality of our data because we don't have another dilution to compare this with. So this is really the only number we have, and we have to take that into consideration. But there's nothing telling us the data are bad. It's just that we don't have as much confidence that the dilution was done correctly. Still, there's no obvious error here, so we analyze the data. So I'm going to choose this one, and go ahead, pause the video if you want to do it first. Probably should. That's going to be 275 colonies, 0.1 milliliters times 1 over 10 to the minus 4. So this is like 275 times 10 to the 5th, 2.75 times 10 to the 7th CFUs per milliliter. I think that's enough for one video, so I will see you somewhere else.